So now let's look at what happens when we bring in a second classification or treatment variable into our analysis of variance. So in the previous airline passengers rating example, there may be other causes of variation. The factors could be the season of the year, particular airport, or even the number of passengers on the flight. So the benefit of considering other factors is that we can reduce the error of our variance. And so if we can explain more of that variation, then we can have less error. Here we have an example of a two-way 5x4 ANOVA. Driver has 5 levels, and each of those levels are the different drivers that we have. And the second way are the 4 different routes. So setting up the problem this way, we're able to do a comparison of all of these groups. If you were to look at this in terms of individual t-tests for comparison between each of those pairs, you would end up increasing your experiment-wise error, which is the risk of one or more type 1 error anywhere in a set of hypotheses tests in a single study using a single group of people. So first, let's conduct a test of hypothesis using a one-way ANOVA. And then we'll bring in our blocking variable in a two-way ANOVA to test a hypothesis that 3 or more population means are equal. So in our null hypothesis, we're going to use the subscripts for each mu, or population mean, denotes the different routes. So US 6 is 1, West End is 2, Hickory is 3, Route 59 is 4. So we have 4 routes, so our number of numerator degrees of freedom is k minus 1, so 4 minus 1 is 3. And there are 20 observations, so the degrees of freedom for the denominator is n minus k, so 20 minus 4 equals 16. So if I use 3 degrees of freedom in my numerator, 16 degrees of freedom in my denominator, and I go to my F distribution table at the 0.05 significance level, I find that the critical value of my F is 3.24. The mean travel time along the routes were 20.6 minutes for US 6, 21.4 minutes along West End route, 25.4 minutes along Hickory Street, 23.8 minutes along Route 59. So we could conclude that these differences could be reasonably attributed to chance. So from the ANOVA, I want you to notice that the sum of squares for the treatment is going to be 72.8. And the sum of squares total is 229.2. So in this case, our treatment is the route that the bus drivers are taking. So when we bring in that second variable, which in this case is going to be our driver, that's going to help to reduce our sum of squares error term by using this blocking variable. And so we're going to use the formula that you have on the screen here to help find your sum of squares blocking. So we look at K as being the number of treatments. B would be our number of blocks. X sub B is the sample mean for the block. And then X sub G is the overall or grand mean. And so this is going to end up reducing our sum of squares error, or SSE, and the computed values of F will end up becoming larger, which makes our p-value smaller. So let's take into account that second variable, or our block variable. So the sum of squares treatment from the drivers is still going to be 72.8. Now let's find the sum of squares for our block variable, which in this case is the driver. The overall mean is found by adding the travel time for all drives and dividing by 20. So we have 456 divided by 20 to get 22.8. So once again, remember that K is our number of treatments, so we have 4 routes. B is our number of blocks, 5 drivers. X bar sub B is the sample mean of the block, B, and X bar sub G is the overall grand mean, and in this case our grand mean is 22.8. So our sum of squares total and our sum of squares treatment will be used from the results that we saw earlier, because those are still not going to be affected by whether or not we look at our blocking variable or not at this point. And at this time, what we see on our ANOVA table, we have sum of squares total still being 22.9 and our sum of squares treatment being 72.8. So, here we see the same format that we had with the two-way ANOVA table as in the as we saw with the one-way case. The difference is now you see the additional row for your blocking variable. And in some software packages, such as the one that this was um, created in, the sum of squares total isn't always shown. Now I know you'll notice on the screen that it says type 3 analysis of variance. There are a couple different ways that variance can be calculated. Type 3 is going to be the most common one. And for the purposes of this course, we don't really need to worry about how the other types are done. But the whole point of bringing in that blocking variable, you now see that the residual or the error variation is now smaller than it was when we just had the one-way ANOVA. But if we want to give the blocks the same status as the treatment, we can do that for our hypothesis testing. And so once again, we're going to use the values in the table to look at our next set of hypothesis tests. So here in this example, we're concerned about the difference in the travel time for our drivers. So we conduct a test of hypothesis of equal block means. So first we test whether the treatment means are equal. Using our F statistic, there are k minus 1 degrees of freedom in the numerator, so 4 minus 1 is 3. And there are b minus 1 times k minus 1, so 5 minus 1 times 4 minus 1. So 4 times 3 is 12 degrees of freedom in our denominator. We go to our F distribution table using the 0.05 level of significance to find the critical value for the first set of hypotheses is 3.49. And to calculate the F statistic, we're going to take the mean squared treatment, MST, divided by the mean squares error, or MSE. And remember, we obtained the value from mean squares treatment and mean squares error in the table on the preceding slide that we saw, but you should also see it on this slide as well. And then we'll use the first letter of each driver's name as the subscripts in our second set of hypotheses. And so here, when you see the calculation of the 7.93, that's where it shows up in our ANOVA table. So here we've got the decision rule where our critical value is 3.26. And once again, we find that using the F distribution table, using 0.05 as the significance level, with our degrees of freedom of the numerator being 4, so b minus 1 is 5 minus 1 equals 4, and the degrees of freedom in the denominator as 12, which is once again found by b minus 1 times k minus 1. So 5 minus 1 times 4 minus 1 is 4 times 3 equals 12. And to calculate our F statistic, we're going to divide our mean squares blocking, or MSB, by the mean square error, which is our MSE. And once again, we just take these values from our ANOVA table directly.